intersecting or overlapping or parallel, then you would have 1, infinity, no solutions. Or you'd call this intersecting, or you'd call this overlapping, or you'd call this parallel. But then we also had some other vocabulary words for it, which was that this was consistent, and this was also consistent, meaning that there is an intersection point. Right? Consistent means you can solve it. There is a point of intersection. Here there's just one, but there's definitely many of them. Whereas here, inconsistent, meaning that you cannot solve it. And then we also said that this was independent because there's only one solution. Independent. This was dependent because each solution for y depends on x. So if I tell you the x value, then you can calculate the y value. So that's dependent. And then this one was also independent, just kind of by virtue of the fact that there is no solution. Independent. Independent. There we go. All right, so those are all the different vocabulary that we've talked about. And then what were the 2 definitions of solving a system of linear equations? This one's very important. What's the first definition of solving a linear equation? I mean, solving a linear system. What does it mean to solve a system? Boy, all of these markers are good. To solve, there we go. To solve a system means?
Visual point of intersection.
Yeah, one's a visual point of intersection that you can see by graphing. Whereas the second definition, and actually the most important definition, is to find what?
Find a coordinate that makes all equations true.
Yeah, find a coordinate that makes all equations true. And here's another way to think about that. We're finding a coordinate. Do you know what that coordinate is? That coordinate is an input, right? We talk a lot about functions and inputs and outputs. That coordinate is the input that will make all of the equations true. Okay, and then we had 5 different methods, and they were graphing, systematic guessing, substitution, elimination, and then today we get to the matrix methods, which are determinants and inverses. Sorry, there are 6, not 5. All right, so here we are. It's November. That's a typo. That's not a typo. That's just not the correct. There we go. Today is the 17th, April 17th. So we're going to wrap up chapter 8 today. And I'd say that's it. Next week we'll do chapter 9, and then you'll take your test. I do have some good jokes for you today, in my opinion. Here we go. What did the janitor say when he opened the janitorial closet? Supplies! I thought that was pretty funny. All right, and I'll give you a bonus joke today because it's the end of the week and I didn't give you a joke on Monday. Have you ever eaten just the jelly from inside a jelly donut? It's filling. It's filling, but it's filling. Okay. All right, I can see we're all ready. So I think we finished number 5, right?
Yes.
We talked about the infirmary, and we nailed that. We got that solution down, right? Or did we finish the problem?
We finished number 5 because yes, there are 8 answers.
But we didn't actually solve. Oh no, we did solve it, didn't we?
Yeah.
Yeah. Okay. So we're done with number 5. Now we're moving on to number 6, which is a fun example of a system of 3 equations. So let's go ahead and take a look. Now, there were a few main ideas that we talked about with a word problem. Okay. One way to approach a word problem is to shut down cry and not try it. Right? That's one way to approach a word problem. Hopefully that's not how we're going to approach it. The second way is to just wrap our mind around it and maybe even try to come up with a and creating your equations and solving from there. So let's just read the problem and see what we think. So we have a collection of 155 coins. So right off the bat, just imagine how kind of exciting that was to sit there and count out 155 coins. Have any of you like rolled coins before? Like you had a change cup and you dump it out on the ground and you sort it into quarters, nickels, dimes, pennies, and then you stack them and count them and then put them into rolls. Have you ever done that in your life? Somehow I did a lot of that in my childhood. I think that affected me. You know, made me like math is what I mean. Right. So you've got 155 coins and you've got nickels, dimes, and quarters. So fortunately there are no pennies. It's just nickels, dimes, and quarters. So I've got nickels, which a lot of us would probably write like 5 cents, and dimes, which we'd say like 10 cents, and quarters, which we'd say like 25 cents. But just like we don't compute in percentages, you have to convert a percent into a decimal. How do we convert with money? I mean, how do we compute with money?
0.05.
Yeah, that would really be 0.05, and a dime would be 0.1, and a quarter would be 0.25. So that's what we're dealing with so far. The total value of the coins is $24.95. So notice how so far they've given us 2 pieces of information. We have 155 coins, and we have $24.95. And that information is going to become our 2 equations. Each of those is going to be an equation. So now they start telling us information. If the number of dimes is 2 more than twice the number of nickels, how many of each kind of coin is in the collection? So first of all, notice that because they gave us 3 unknowns, we're going to have 3 equations. Because remember, you can only solve 2 variables if you have 2 equations, and you can only solve 3 variables if you have 3 equations. So we know we're going to have 3 equations. Do you think that we could try to guess this answer? This would be kind of tricky. Let's just make a little column here. So I've got nickels, dimes, and quarters. Let's see if we can make a guess, all right? What we know for sure is that the number of dimes is 2 more than twice the number of nickels. Okay, so if I have 0 nickels, what's 2 more than twice nothing? 2. Yeah, if I have 1 nickel, 2 more than twice a nickel. So first I double it and then add 2. That's really what we're doing to find the dimes. Double this number and add 2. So double it, add 2, that'd be 4. Double it, add 2, so 2 doubled is 4 plus 2 is 6. If I had 3 nickels, double it, that's 6 plus 2 is 8. If I had 4 nickels, double it is 8 plus 2 is 10. This is a little laborious and mind-numbing, right? If we really wanted to list out this whole thing. I could keep going. If I had 5 nickels, double it is 10 plus 2 is 12. But again, it's helpful to at least wrap our mind around the fact that whatever number of nickels we have, so if I just call that n, how many dimes do I have?
Plus
2n plus 2. And notice that by writing this down, I just came up with an equation for D. Dimes are equal to 2n plus 2, right? Double it plus 2. Okay, that's what we have so far. Then how many quarters do I have in every case? You know, if these are the numbers for nickels and dimes, how many quarters do I have? Yeah, I'd have to subtract from 155, right? So 155 minus 0 and 2 would be 153 quarters. And 155 minus 5 would be 150 quarters. And then that 2 and 6 is 8. 155 minus 8 is 147 quarters. And then 8 3 is 11. 155 minus 11 is 144. And then 4 and 10 is 14. 155 minus 14 is 141. And you can kind of see how that table is going to end up looking. I could also come up with an equation for quarters now, couldn't I? Because the number of quarters is 155 minus that and that. So just take a look. I could do the number of quarters is 155 minus the number of nickels, and then minus the number of dimes, which is 2n plus 2. So now I have for quarters 155 minus n minus 2n minus 2, which 155 minus 2 is 153 minus 3n. So now that's my number of quarters, 153 minus 3n. 153 minus 3n. Am I doing this right? Is this all making some okay sense? Now, of course, we're not doing the problem the way we're supposed to be doing it yet. We're just playing. We're just playing with a table and seeing if we can come up with some possible information. Now, notice that if I wanted to, I could now go ahead and say this plus this should equal what? The number of nickels plus the number of dimes plus the number of quarters should equal what? Well, that's in money. We're talking about numbers of coins. Yeah, that plus that should equal the number of coins. So let's try it. If I do n plus 2n minus 2 plus 155 minus 3n, that should equal 155. Which I think this is going to be kind of hilarious. 1n plus 2n is 3n. And then minus 2 plus 155 is, oh.
Is it 150?
Oh, sorry, yeah, that was 153. Thank you. So then 150. Oh, that's plus 2. There we go. Yep, so that's 155. And then minus 3n. And what happens? Did I solve anything? It actually didn't produce a solution for me, did it? It just told me that it's true. So by playing around with this table, even though I do know now that whatever number of nickel I have, that'll tell me the number of dimes, that'll tell me the number of quarters, that alone is not enough for me to actually solve the problem and now how many nickels I have. It was fun to play around with. And this goes back to the fact that in order to solve for 3 variables, you need 3 equations. And so far, I don't have enough information to solve the problem. Okay, so do we have a guess for how many quarters and how many nickels and how many dimes we have? Not really yet. I could go ahead and just try one of these. Like, why don't I just take this and multiply it times a nickel, and take this and multiply it by a dime, and take this and multiply it by a quarter? Then where would I be at? 4 times 0.05 plus 10 times 0.1 plus 141 times 0.25. And that gives me a total of $36.45. Am I in the ballpark? Yeah, I suppose $24.95 is what I should have, and I have $36.45. So how do I bring $36.45 down? What would I need less of? I want to bring the total dollar amount down. Yeah, I would need a lot less quarters, right? I mean, right now I'm very quarter heavy. I have tons of quarters and barely any nickels and dimes. So I really need to flip-flop this whole thing and have far fewer quarters, and that would bring down the overall dollar amount that I have. Okay, so what does that tell us? Well, by the time we're done solving the problem, we should have much less quarters than 140 and much more nickels and dimes. But that's all we really know. Folks, right now, all we've really just done is kind of play around with the problem. And while you might be saying, Mr. G, get on with it. Let's set up 3 equations and solve it. I want to suggest to you that a good way to start a problem is to at least start playing around with relationships and see how the problem feels. Okay, but now that we've played around, we don't really have a strong guess, other than the fact that we can't have very many quarters, because that makes the dollar amount too much. Now let's go ahead and try the problem. So what's our first step? What's the first thing we do?
Define variables.
Yeah, define our variables. And where do we look to define variables? Yeah, in the question. So it says, if the number of dimes is more than twice the number of nickels, how many of each kind of coin is in the collection? So the question is, how many of each coin? So we'll go ahead and say, now folks, should we say X, Y, and Z? Or should we say N, D, and Q? Probably N, D, and Q, because then we know immediately what we're talking about, right? Why should we use X, Y, Z and then have to make a mental note that X is nickels and Y is dimes and Z is quarters? We could just go ahead and say, let N be the number of nickels, and then D is the number of dimes, and Q is the number of quarters. Now, how did I know that N should be the number of nickels rather than the value of a nickel?
It's asking a question about the collection.
Yeah, the question is saying how many of each kind of coin is there. So we already know, they're asking for how many coins. But also, is it unknown the value of a nickel? No, we all know the value of a nickel is 5 cents. So it would be silly to say that N is the value of the nickel or even the dollar value of all the nickels. What we're talking about is the number of nickels. Okay, so there's our variables. Now let's move on to step 1. And that would be to create our equations. And remember, when you create equations, you want to try to label them and say what they are in English so you know what you're talking about. What's our first equation going to be? What's the first piece of information they gave us? The fact that we have 155 coins. So that right there is going to be, the first equation is total number of coins. And sure enough, the equation, N plus D plus Q, is going to equal the total number of coins. So the information they give you is almost always the thing that you set equal to on the other side. And as you can see, we almost always have an equation that's x plus y plus z, or x plus y. There's almost always an equation that just sums the variables. Okay, so then what's our second equation? Total what?
Total value.
Yeah, the total dollar value. So the total dollar value of our collection, now how do we write that down? What will that equation look like?
Is that the one where it'd be 0.05?
Yeah, exactly. And probably, I think in every word problem we've done so far, the first equation is just adding the variables. And the second equation is putting a coefficient in front of each variable according to the numbers they gave us. So our coefficients would be 0.05n because a nickel for 5 cents, 0.1d because a dime for 10 cents, and 0.25q because a quarter is for 25 cents. And then the total value is 24.95. It's very formulaic, isn't it? I mean, at the very least, what we should say is they're giving us word problems that are very formulaic, that we're always setting them up in the same way. First, you add up all the variables to be the total, and then you add up the weighted variables with coefficients. And then what's our third equation going to be?
Number of times is 2 minus twice the number.
Yeah. Now this last one, in math textbooks, you'd call this a constraint. The constraint. We are constrained by the information that the number of dimes, now watch how I'm going to write this down. I'm just reading a sentence. The number of dimes is 2 more than twice the number of nickels. I hope you noticed that just reading it in English directly translated it into a math sentence. Right? By just reading the sentence, the number of dimes is, because is always means equal to, 2 more than twice the number of nickels. So I already wrote down my equation essentially. By just reading and writing at the same time, I now know that D equals 2 plus 2n. And that's my other equation. Okay, so now what do we do?
You would substitute D for 2 plus 2n.
Yeah, that's certainly a good approach. We could go ahead. Now, there's a few things we could do. First, we could make this equation look like the equations we already have. Like the other equations are n plus d plus q equals a number. So I could move the n over to the other side, and I could have the equation negative 2n plus 1d plus 0q equals 2. And that way, this equation looks like the other ones. Right? Now they all look like something n plus something d plus something q equals 2, just to make everything look very consistent. You don't have to, but you could. And then the other thought is, remember, we have 3 variables in 3 equations. What's our first goal? Yeah, to take one of them out. That sounds like a gangster mafioso thing. Yeah, take one of them out. So we want to go from 3 variables in 3 equations. We want to get down to 2 variables in 2 equations. And then we want to get down to 1 variable in 1 equation. So we're working our way down from the number of variables. And yes, by just substituting 2 plus 2n in everywhere that you see a d up here, then that means that you'll have these top 2 equations in 2 variables. And as soon as you get to 2 variables and 2 equations, you can just solve like normal. So let's try it. We're going to substitute 2 plus 2n into both of those other equations for d. So let's do it very carefully. First, I have n plus d plus q equals 155. And I'm going to substitute in for d. So now I have n plus parenthesis plus q equals 155. And I'm going to plug in 2 plus 2n where d used to be. This is a fun problem because we're going to use substitution to reduce our problem from 3 variables to 2 variables, and then we can use elimination to solve the 2 variable equations that we have. So what do we have here? Combining like terms, we have 3n plus q plus 2 equals 155. And what should I do with the 2?
Subtract it over.
Yeah, might as well move it over to the other side. So we have a normal looking equation. So 3n plus q equals 153. So that's one 2 variable equation that we now have. So now let's look at the other equation. Now, first things first, do we like looking at this equation, 0.05n plus 0.1d plus 0.25q equals 24.95? Do we like all those decimals? Maybe you do, maybe you don't. How can we get rid of all the decimals? Yeah, we could either multiply the whole equation by 100, because that has the effect of moving all the decimal places to the right, or we can just say, move all the decimal places to the right. You're allowed to use either method. So let's go ahead and first start by moving all the decimals to the right. So that would actually be 5n plus, very careful here, if we move the decimal twice to the right, that's 10d, and then plus 25q equals 2,495. So the first thing you could do is you tell yourself either I'm going to multiply the whole thing by 10, or I'll just move all the decimals twice to the right, both of which are legitimate. So now we'll do the same thing. We'll substitute our 2 plus 2n in for d. So I've got 5n plus 10 times something plus 25q equals 2,495. And we're plugging in.
Are you multiplying by 10 or are you multiplying by 100?
I'm so sorry. Thank you for asking that. By 100. Yeah, definitely by 100, right? We want to move the decimal twice, so you have to multiply by 100. So now we have a little bit of work to do. Since we substituted, we have to distribute. So 5n plus 20 plus 20n plus 25q equals 2,495. And then we can combine like terms. Now we have 15n plus the 25q plus the 20. But we don't want to keep 20 over there. We want to push the 20 over to the right-hand side. And so then we have the two-variable equation, 15n plus 25q equals 2,475. And that's our other two-variable equation.
Would it be 25 then?
Would you add a 5?
Oh, sorry. Boy, I'm making a couple mistakes here, aren't I? Now, is that better? You have that right? I'm keeping you all on your toes. You're keeping me on my toes. Okay, now right about now, you might ask yourself, do you feel uncomfortable by using n and q instead of x, y, and z? If it makes you feel uncomfortable, do the whole problem in x, y, z. Right? You're allowed to use whatever variables you want. I just chose to keep n, d, and q because that way I don't have to remind myself later on what x, y, and z represent. Okay, so philosophically, folks, what did we do? We defined our variables, we created our equations, and then we knew from a philosophical perspective that we have to take a 3-variable, 3 equations down to 2-variable, 2 equations, and we have done it. We now have 3n plus q equals 153, and 15n plus 25q. Oh, 25, jeez. No, we're going to start throwing things at me. I did tell you that the students threw something at me once, right? Did I tell you?
Yeah, but then you said you never said.
I've never said it again. Okay, so now we have our 2 equations. Now, which variable do we want to eliminate? We could, well, eliminating the n wouldn't be very convenient, would it? Because 3 doesn't go into 25. So to eliminate positive 25n, I would need a negative 25n, but 3 times nothing equals 25. So let's not eliminate n. How about q? I have a positive 25q. Could I make that a negative 25q? Yeah, pretty easily. So let's go ahead and multiply this equation times negative 25. And that'll give us negative 75n minus 25q equals 25 times 153. Negative 3, 8, 2, 5. There, so now our q's cancel out, and we have negative 50 and equals 2475 minus 3825. Negative 1350. Now, folks, when we finish dividing right now, should we get a whole number for n, or can we get a fraction for n? Can n equal a fraction or a decimal? What does n represent again? Yeah, so it better be a whole number, right? If you got a decimal, what would you do? Well, but even if you got a decimal or fraction, what would you do? You'd go back and find your mistake, right? Because you can't have a partial number of nickels. And so indeed, when we divide by the negative 50, we do indeed get a whole number. So that's good. If you had gotten a decimal, you would have to say, geez, I must have made a mistake. Yeah, so the number of nickels is 27. Now remember what I did earlier? When I set up my nickels, dimes, and quarters, I said n was my number of nickels, 2n plus 2 was my number of dimes, and 153 minus, was it 3n? Yeah, was my number of quarters. So already based on my previous mode of thinking, I think I can go ahead and figure out how many I have of all. So that if that was 27, then if I double it, that's 54 plus 2 is 56. And then if I subtract both of those from 155, then I think I have my answer. I think I do anyway. And if I check all that by actually multiplying out 5 cents times 27 plus 10 cents times 56 plus 25 cents times 72, sure enough, that does give me the 24.95. I just say that as a quick kind of thought check that I know that what I'm doing over here worked out because I was able to check it according to my previous thinking. In any case, we're not done. Now that we have n is 27, what do we have to do? Now that we know that nickels is 27, what do we do? Yeah, now remember, this whole rest of the process is now called back substitution. We work our way back up the problem so that we can solve for both other variables. You'll notice now that we have n, we can easily plug back in and solve for q, right? So that's the first back substitution. What do you want to plug n into? 3n plus q or 25n plus 25q? Probably this one, because the numbers are smaller. So let's back substitute n into that equation. Q equals 1. And so 3 times 27, that's 81 plus q equals 153. And subtracting 81 from both sides, we have q equals 72. That's good, because that's what I was expecting over here. Now that we know n and q, we back substitute again, but all the way back to the original. All the way back to one of our original equations. Which one should we substitute in for? We know n and q. How can we solve for d? That's helpful to think. Our goal is to solve for d. You could plug it in the total there, and plug in for n and q, and then you have a d. What else could you plug it into? Where can I plug my n and q in for? I can plug it into this one, but that'd be wildly inconvenient. It's got all those decimals, tons of numbers. Why bother? Well, look at this equation. That's already solved for d. And all I need to plug into it is that. So probably that would be the most convenient one to plug into, you know, in terms of back substituting. So now I can just go ahead and say that my d, I don't think anybody used this line anyway, my d would be 2 plus 2 times the number of nickels, which is 27. And so that's 2 plus 54, which is 56. So now we think we have all 3 answers. One thing I definitely am very much aware of as I look at the board is that there's a lot going on, isn't there? You're moving around in different places to do your work. Like, we started very nicely by putting our variables in our equations, and then we had 2 different derivations to do to eliminate a variable and get down to 2 variable equations. And then from there, I did my elimination to get 1 variable. And then once I had 1 variable, this space is where I got my 2nd variable, and this space is where I got my 3rd variable. So, you know, when you're showing work on your own paper, it can be tough to follow where all you're doing your work, and maybe it'd be best to never go back and rewrite over something you already wrote on, but just simply going down and writing more below it. In any case, is our answer correct? How do we know it's correct? You did check it? Well, let's check. I mean, there's only 3 equations to check. If we add them all together, do they make 155? So, again, this is something you do in a calculator. 27 plus 72 plus 56. That's 155. That equation is correct. And then I have to actually plug them all in to all that nickel dime stuff, which I already did over here. So that one's correct. And then sure enough, d does equal 2 plus 2n, because that's how I solve for d. So yeah, all 3 equations are correct. That's quite the process. Questions, thoughts, feelings? You'll definitely have 1 or 2. You'll have a 3 variable, 3 equation problem on your practice test, and you'll have a word problem of some sort on your practice test. And of course, there'll be more of these on the More website for you to practice as well. I think that's it. You know, I'm thinking, is there a good way to check your answers? Like previously in the whole rest of this course, I've said any equation you have, you can just graph it on Desmos, and you can find the answer by looking at the x-intercept. But in 3 systems of 3, sorry, a system of 3 equations, there's no quick place you can go to check your answer. The only way you can check your answer is really by just plugging the numbers that you get into the three equations and seeing if they're right. All right. Well, I guess we're done with that. The rest of today is going to be focused on matrix methods. So once again, does everyone have a graphing calculator? So it looks like everybody does. Victor, you have one over there? Oh yeah, there it is. Okay. Yeah. Okay. And Isaac, do you have a graphing calculator? Okay. All right. Good. So what we're going to look at is matrices, and just taking a look at that next page of matrix arithmetic, you see a box essentially, or brackets, with a grid of numbers. And you might be wondering, well, why on earth would we be interested in a grid of numbers? Well, let's just consider this system that we just wrote down. This system of quarters, nickels, and dimes, if I look right here, got this. Okay, then I would say that I have 1n plus 1d plus 1q equals 155. And I had 0.05 n plus 0.1d plus 0.25q equals 2495. And then recall I said that if we move the n over to the other side, we can write it in a more, so it looks like the other one, so it'd be negative 2n plus 1d plus 0q equals 2. So then I can write down negative 2n plus 1d plus 0q equals 2. So what you do is you put your system in the same structure. So you have n stacked on top of n's, your d variable stacked, your q variable stacked, your equation sign stacked, and the numbers stacked. And then you simply create a bracket, and you just take all the coefficients. So it'd be 1.05, negative 2, and then 1.11, and then 1.25, 0, and 155, 2495, and 2. And oftentimes what we'll do is we'll draw a vertical line right there to kind of distinguish that these are the coefficients of the variables, this was where the equal sign goes, and these were all the numbers that those equations are equal to. So first things first, that's just what a matrix is. A matrix just strips away all the variables and the equal signs and just gives you the coefficients, which are the only things that really matter, is the coefficients in front of the variables. So that's where we would get a matrix from. What could the matrix represent? Anything, right? It could represent absolutely anything. My favorite example of what a matrix could represent would be how many, so let's see, this is Monday, Tuesday, Wednesday. I'll just do Monday, Wednesday. Monday, Tuesday, Wednesday. This could represent the number of cookies that I eat on different days. So I've got chocolate chip is the first row, peanut butter cookie is the second row, and I can say on Monday I had 2 chocolate chips, 1 chocolate chip, and then 3 chocolate chips. And then on Monday I had 3 peanut butter cookies, 2, and then 1. And so what does this matrix represent? It just represents the total number of cookies I ate on the first 3 days of the week. Kind of important that you have the row labels and the column labels so you know what you're talking about. Because if I just showed you the grid of numbers 2, 1, 3, 3, 2, 1, it could represent anything in the universe. You'd have no idea. But by telling you what the rows represent and what the columns represent, you now have just a grid of information. So that's another thing that a matrix could represent, is just data, right? So it could represent a system of equations. It could represent just pure data. What we're going to be doing is using a matrix to represent a system of equations, and then your calculator will actually solve the system for you. Isn't that wonderful? The calculator will solve the system for you. You don't have to do elimination or substitution. You just plug it in your calculator, and it tells you the answer. So the first thing we want to do is just do some basic arithmetic with matrices and see how they work. And namely, the first thing you need to know is that you can really only add and subtract matrices if they're the same size. They have to have the same number of rows and the same number of columns. So let's go ahead and take a look up here. They gave us matrix A, B, C, D, and E. First things first, let's talk about the size of a matrix. I say they have to be the same size. Just all the way up the top there, the definition. Size is given by row by column. The number of rows times the number of columns. So if we look at the size of matrix A, that would be how many rows? 2 rows, and then how many columns? 2. So the size of matrix A is called a 2 by 2 matrix because there are 2 rows and 2 columns. Likewise, the size of matrix B is also 2 by 2 because there are 2 rows, 2 columns. The size of matrix C is also 2 by 2 because it has 2 rows. Oh, nope, sorry, I need to keep looking at that. C is not 2 by 2. What is C? Yeah, it's 2 rows, 3 columns, so 2 by 3. And then the size of matrix D, yeah, it's 3 rows, 2 columns, so 3 by 2. And the size of matrix E is 3 by 3. So, first off, you can only add and subtract matrices if they're the same size. So, you can add and subtract if they are the same size. That's a nice little note to ourselves. So let's go ahead and try that first addition problem. In fact, we'll do number 1. Yeah, we'll do number 1 first. So number 1, we have the matrix. We have the matrix E plus D, which E. Oh, well, what a silly question for us to have. Can we add E plus D? No, we cannot. You literally A plus B makes a lot more sense. A and B we can actually add together. So with matrix A plus B, I would take my matrix 1, 2, 3, 4, and then add it to matrix B, which is 0 and -3, -5, and 2. And when you add matrices, you just add all the individual positions. So you would add the upper left position, 1 plus 0 is 1. Add the upper right position, 2 plus -3 is -1. Add the lower left position, 3 plus -5 is -2. And add the lower right position, 4 plus 2 is 6. So matrix addition and matrix subtraction is very simple because you just do it entry by entry by entry. Just for fun, let's try another one. What if we did B minus A? If we did B minus A, we'll have to be a little more careful because there's a subtraction sign. So B is 0, -3, -5, and 2. And then we're going to subtract the A matrix, which is 1, 2, 3, 4. You have to very carefully keep track of the fact that you're subtracting. So in the first position, upper left, 0 minus 1 is -1. And then the second position, upper right, -3 minus 2 is -5. And then lower left, -5 minus 3 is -8. And then lower right, 2 minus 4 is -2. So when you add and subtract, you just do position by position. With matrices, there are 2 ways to do multiplication. Now, first of all, we don't ever do division. Maybe that's nice to know. We basically never do matrix division. But we do matrix multiplication, and there's 2 ways to do multiplication. One is called scalar multiplication. And scalar multiplication means you multiply every entry by the same number. So that would be like the number 2. The number 2, they're asking us to find 10C. That just means that we're going to take matrix C and multiply every single entry by 10. So I would take my 10 right in front of the matrix C, which is 10, 11 halves, 0, 3/5, 5, and 9. And I'm just going to multiply every single entry by 10. So again, you can do that in your head. You can do each multiplication on your calculator. So I'm going to take 10 times 10 is 100. -11 halves times 10, I'll just write -111 over 110 over 2. 10 times 0 is 0. 10 times 3/5 is 30/5. 10 times 5 is 50, and 10 times 9 is 9. Notice that when I multiplied 10 times each fraction, I just multiplied 10 times the numerator. Right? That's one way to quickly multiply a whole number of times a fraction, is you just multiply the numerator. Of course, I should still go back and simplify those numbers. I didn't simplify them yet. I just got the multiplication done with. So my answer then would be 100, negative 55, 0, 6, 50, and 90. And that would be the product 10C. Did I do that right? Okay. Now that's called scalar multiplication. And so far that covers everything that we can do by hand. Is you can add matrices by hand, you can subtract matrices by hand, and you can do scalar multiplication by hand. The next thing we're going to look at is matrix multiplication. Which you can do by hand. We're not going to. It's so much easier to do it on a calculator. Right? If we wanted to look at matrix multiplication by hand, we would basically need to devote a whole hour to it, just to see how to multiply two matrices together. Whereas doing it on your calculator, it goes very quickly. So can do matrix multiplication if, so we're going to multiply like matrix A times matrix B. And I'm going to show you that the first matrix, let's say that it was, I'll just give an example. If the first matrix is 4 by 3, if that's the size, so I'm using the size notation, and the second matrix was 3 by 2, okay? Now this is confusing because x means multiply, but this x means size, right? So when we talk about the size of a matrix, we use an x. That's not really multiplication. It's just doing like base times height, length times width, row by column. So we're going to take this matrix and multiply it by this matrix. You can only multiply matrices if the middle two numbers are the same. So that means that the row by column, the column of the first matrix, the number of columns of the first matrix has to be equal to the number of rows of the second matrix. But it's very specific. So if you want to multiply two matrices, the number of columns of the first matrix has to be equal to the number of rows of the second matrix. And by just writing the size of the first matrix times the size of the second matrix, you just need to be able to visually check real quick that the middle two numbers are the same. And then you can say, okay, I can proceed and I can multiply these matrices. The result of that matrix multiplication is going to be the row of the first matrix and the column of the second matrix. So this is kind of interesting. When you multiply matrices, if you start by multiplying a 4 by 3 matrix times a 3 by 2 matrix, first of all, you can only actually multiply them if the middle two numbers are the same. And then the resulting matrix, the size is going to be a 4 by 2. So that's just the definition of whether or not you can multiply matrices. And if you can multiply the matrices, the result will be that size. I will do some examples so you can see how it works. So, number 3 gives us a matrix multiplication problem. So in number 3, we're going to multiply A times B. And the first thing I'd like us all to do whenever you're going to multiply matrices is check to make sure that the sizes work out. So what was the size of A? Yeah, 2 by 2. And the size of B? 2 by 2. Are the middle two numbers the same? Yes. And so the result is going to be a 2 by 2 matrix. So we already know that, yes, we can multiply matrix A times B, and we know that the result should be another 2 by 2 matrix. So I'm going to write it down. Even though we're not going to do it by hand, I'm going to write it down. So if I multiply 1, 2, 3, 4 times the matrix, 0, negative 3, negative 5, 2, I know I should get another matrix that's 2 by 2. Now the question is, what are those answers? The naive thought would be that you just multiply entry by entry, like 1 times 0 is 0, and 2 times negative 3 is negative 6, and 3 times negative 5 is negative 15, and so on. But that actually is not the answer. That is how you do addition and subtraction, but it's not how you do multiplication at all. So let's see how it works on our calculator. Everybody, calculator ready. This is a lot of steps we're going to do on the calculator. So everybody follow along with me. Like absolutely follow along with me. If you wait like even a minute, you're gonna be too far behind to be like able to follow along. So everybody, you all have your calculators in your hands? Yeah? Yeah? Okay, first things first, you should all, I don't think you have a button that says matrix, but if you look at the X inverse button below the math button, the X to the -1 button, the little yellow or blue writing above it says matrix. Right, so first of all, you don't even have a button that just says matrix. It's a sub-option of a button. So you'd have to hit second X to the -1. And that'll call up a screen, which is your matrix screen. So I'm going to put up what I see on the board here and make sure you see what I see. So on my screen now, what I see is names, and then I see math, so hilarious, and then edit. And then going down the side here, I have 1, 2, 3, 4, 5, and I have matrix A, matrix B, matrix C, and so on. And maybe you already see some sizes. Do you already see some sizes on your calculator? Maybe not if your calculator's never been used for matrices before. But I see some sizes like 2 by 2, and 2 by 1, and 3 by 3. So what this tells me is that in my calculator, I already have matrix A is a 2 by 2, and matrix B is a 2 by 1, and matrix C is a 3 by 3, and so on. I can clear all those out though. So here's what we're going to do. Everybody, your cursor should be on matrix A, right? And then push twice to the right and go under edit. And once you get to edit, matrix A is already highlighted, that's matrix number 1. Then enter, and it's going to take you into a screen that says, I think I can erase this now. It's going to take you to a screen that says matrix A, and the first thing it gives you is the option to change the size. So I don't know what you already have there. Mine already says 2 by 2. That is what I want, but just for fun, I'm going to hit 2, enter, 2, enter. Okay, you hit the number you want, enter. Number you want, enter. So does everyone have 2 by 2 now? Okay, now the cursor automatically went over to my matrix. And follow the cursor. It's going to start at the upper left, and it's going to go right, and then down, and then right. So it's just like you read a book. It's going to fill in across the first row, fill in across the next row, fill in across the next row, just like you're reading a book. So now we're going to type 1, enter, 2, enter, 3, enter, 4, enter. Everyone try it. 1, enter, 2, enter, 3, enter, 4, enter. And you should see your matrix appear. So now everyone should be looking at a 2 by 2. It should be labeled 2 by 2. If it doesn't say 2 by 2, I have no idea how to instruct you on this Casio, but I have a TI. Do you want to borrow a TI? Folks, in order to follow along with the discussion, you might want to borrow one of my TIs. So, matrix right there. Now you're in there, so I'm going to go to edit. And enter. I go ahead and start editing. So 2, enter, 2, enter, type there. Okay. As I walk around, please let me know if you have any questions. Just quickly take a look. If you don't like, poke me or yell at me, I'm assuming that you're good. Everybody has their matrix uploaded? Hey. Oh, where's your matrix button? Oh, gee whiz, I have no idea. I've never used this one. Can I give you one of mine? Okay. Because if I give you one of mine, you can use it for the test. Okay, did it work? So that says 2 by 22. We want to go back up and just make it 2 by 2. So let's clear that out and just go 2. There we go, enter. Now you just have a 2 by 2. So now you can have 1, enter, 2, enter, 3, 4. Because the cursor's already here. Look at that matrix A. You want to put in 1, 2, 3, 4. So you have 1, enter. There you go. 1, 2, 3, 4. That's what you want. Okay, everybody else? Okay. So everybody, we're all looking at matrix 2 by 2, and you all have 1, 2, 3, and 4 in there, right? Okay. So now at this point, the safest bet is to hit second quit. So second mode or second quit. That takes us back out of the matrix area, and then just go right back in again. So hit second X to the -1. And you're right back into your original matrix screen. Looking here. And now for sure you have matrix A entered correctly as 2 by 2. Now let's edit matrix B. So once again, you have to go over to edit first. You can't go down to B yet. Go over to edit first, and then go down to matrix B and highlight it and hit enter. And you'll probably have to change the size. So So make it a 2, enter, 2, enter. And then put in the matrix 0, negative 3, negative 5, 2. 0. So this time around, everybody should have the matrix B, 2 by 2. And once you're done typing it in, it should be 0, negative 3, negative 5, 2. Did we do that correctly? Yeah. Okay, let me know if that works. Flag me down. Let me know. Or did you get it? And once you enter it in, you can go second quit, second matrix, and go back into the normal screen. That works. Is it working too? Great. Yeah. So first you have to go to edit. Then you go down to matrix B. Yeah, first you have to go to edit, and then 2 by 2, and then you start typing things. So 0, negative 3, 5, 2. So once that's all in there, again, second quit, and then second matrix, go back in. We all now have matrix A and B correctly inputted into our calculator. So here's the really exciting part. Now, we're going to go back to our normal calculator screen. It's second quit. And first of all, clear it out. Like if you had any other previous calculations there, just get rid of it. So you should just see a little blinking cursor. That's sort of our normal calculator screen. So now what we do is we want to multiply matrix A times matrix B. So you go into the matrix, and now we're under names, okay? We're no longer editing. We're not editing anymore. We're going to use the name, and just choose matrix A. It's already highlighted. Just hit enter. And it'll take you right back to your calculator screen, and you'll see matrix A there waiting for you. Now hit multiply, the normal multiply button, just like you're multiplying 2 times 6. And now go back into the matrix again, and under names, push down and choose matrix B, hit enter. And now you're on your normal calculator screen, and you see it says matrix A times matrix B. So first of all, does everybody have that? Yeah, nice. So you're going to go into matrix, and then the first name, A, and times, go back to the matrix, second name. There you go. Okay, did it work? Once you have A times B on your screen, you can go ahead and feel free to hit enter so you can see the result. Super. Yeah, if you have it there, go ahead and hit enter and see what the answer is. You'll notice that the answer is not the entry by entry multiplication that our naive sense would have told us. I'm not using naive in an insulting way, by the way. Naive means what you think. It doesn't mean that you're naive, like silly. It just means that even though you add entry by entry, you don't multiply entry by entry. And so what's our answer? Negative 10, 1, negative 20, and negative 1. Okay, did everyone get that? All right. Well done, everybody. You have multiplied 2 matrices on your calculator, 2 matrices. Now, just in case you're curious, okay, how did this magic work? What are you actually multiplying? I'll show you real quick. You don't have to know how to do this, okay, but I just want you to know. To find, okay, I am going to show you. Everybody watch. Where'd my eyes go? To actually multiply matrices, and this is why it's such a tricky thing. It's so much easier with the calculator. To find the first entry, you multiply the first row by the first column, multiplying and adding as you go. So it'd be 1 times 0 plus 2 times negative 5. So it'd be what? I'll show you the whole thing. To multiply matrices, you'd multiply the first row and the first column. Well, okay, I want this entry right here. So that would be the first row and the first column, because that's the first row and the first column. So that would be 1 times 0 plus 2 times negative 5. 1 times 0 plus 2 times negative 5. Now I want this entry. That would be the first row, second column. So first row, second column, that'd be 1 times 3 plus 2 times 2. Sorry, 1 times negative 3 plus 2 times 2. That'd be 1 times negative 3 plus 2 times 2. Now I want this entry, which is the second row, first column. So second row, first column, that'd be 0 times 3 plus 4 times negative 5. Now I want this entry, which is the second row, second column. So I did the second row, second column, maybe 3 times negative 3 plus 4 times 2. Whew. All right. So first of all, I hope you can appreciate that this is a full contact sport, because you got to like use your hands to know which row and which column you're in. And you have lots of computations to do. And then finally, that's negative 10. That's negative 3 plus 4, 1. And that's negative 20. And that's negative 9 plus 8, negative 1. There. Is that the matrix we got? Okay, yeah. So anyway, if you'd like to learn how to do matrix multiplication by hand, you certainly can. I'd be happy to show you how to do it. You totally don't need to because you can use your calculator, okay? So let's try another one. It wants us to do a minus 2b. Well, this one you can actually do by hand. Because scalar multiplication you can do by hand. You just multiply the b matrix times 2. And then a minus 2b, you just subtract entry by entry by entry. So I'm not going to do this one with you. I won't do this one with you either, because here again, you just take the b matrix, multiply every entry by 7, take the a matrix, multiply every entry by 4, and then you subtract. So again, you can all do that. But let's do a squared minus b squared. That's interesting. So what that really means is, in number 4, that's going to be a squared minus b squared, which is really a times a minus b times b. And anytime you're going to multiply a matrix times a matrix, you would need your calculator. So you would just go back in now and you can type in matrix A, and then literally squared, and then times matrix B, and then squared. And it should give you this answer. 5, 148, 5, 328.
You said matrix A times matrix B.
Well, I'm sorry, a squared minus b squared. So that'd be a times a minus b times b. And I did, let me show you what I did. On my calculator screen, I have a squared times b squared.
Oh, I see. It's subtraction.
Oh, it's subtraction. Oh, man. Thank you. Now I see what you were saying. Yes, okay, that's a totally different answer. Yeah, a squared minus b squared. And that gave me negative 8, 16, 25, and 3. Okay, well, at this point, you might be looking at all this saying, all right, Mr. G, this is fine. I mean, we're typing things into our calculators. It's giving us results. It doesn't necessarily make sense why those results are appearing. What is this good for? By the way, should I go back and do either 4 or 5? We're okay to move on? Okay. Oh, well, actually, I mean, we're about to actually try. Oh, no, okay. In fact, yeah, let's do these inverses before we go for our break. This is perfect. So this is really what we're interested in doing. The next page talks about matrix inverse. So what is the inverse of a matrix? So first of all, we already have that first matrix inputted into our calculator. Everybody, you still have this as your A matrix, right? Yeah. So when they say find an inverse, first of all, I'm just going to show you how to do it on your calculator. So everybody, on your calculator, you're just going to go to your calculator screen and put in matrix A. There's the A matrix. And then the very button that you've been pushing all along to get to the matrices is x to the negative 1. Push that button. And it shows A to the negative 1. And that's exactly what we want to compute. That's called A inverse. Notice that makes sense because we were talking about a function, and then we were talking about the inverse of a function, which is f to the negative 1. That's f inverse. And so now this is A inverse, not A to the power of negative 1. It's not a reciprocal, it's an inverse. So if you get A to inverse, what do you get? Hold on, that's not what I got. A matrix A. Oh, how did my matrix change? Oh, this is bad. Did everyone get that result previously?
Yeah.
Gosh, my matrix A is now completely different. 1, 2, 3, 4. Okay, let's try that again. Yes, the answer was negative 2, 1, 1.5, and negative 0.5. Did everyone get that? So that's A inverse. One more really fun trick I want to show you all. Right now you can hit math, the button right above it. Hit math frac. I think you've tried math frac before. It turns your inverse, or it turns your matrix into fractions instead of decimals. I'm not saying that's key. It's just nice. So once you get a matrix answer and it gives it to you in decimals, you can still math frac the matrix and it will turn every decimal into a fraction. That's kind of nice. Okay, so that's an inverse. You'd simply do the matrix and then hit x to the negative 1. What does that mean? What is an inverse? Well, an inverse for a matrix means the same thing that we've done with inverse operations. So recall, inverse operations are operations that cancel each other out. So like plus and minus are inverse operations, multiply and divide are inverse operations, square and square root are inverse operations. But most importantly, an inverse operation can help you solve an algebra equation. So if I have the algebra equation 3x minus 2 equals 4, right? Then we would solve this algebra by doing the inverse of each operation. So x is being multiplied by 3 and subtracted by 2. The inverse of subtracting by 2 is adding by 2. And the key is that it cancels itself out. So now we have 3x equals 6. And then the inverse of multiplying by 3 is dividing by 3, which is x equals 2. Now here's what's even more interesting. Not about adding and subtracting, but multiplying and dividing. If I have 5x equals 20, this is a very simple algebra equation. X is being multiplied by 5. So you would divide by 5. Here's the most important part. What happens when I actually divide by 5? What does this become? Yeah, I mean, we always cancel it out, but actually it becomes 1, right? Not so with addition and subtraction. When you add and subtract inverses, they become 0. But with multiplication, we cross them out as if it goes away, but really it always becomes 1. And so when we do matrix multiplication, when we talk about an inverse, we're talking about a matrix that you can multiply by the original matrix to equal 1. So here's what we would expect. If I right now took matrix A times matrix A inverse, it should equal 1. Because we're essentially saying that, that the inverse is like dividing. So if you're, yeah, it is essentially like dividing. So the inverse of multiplication is division. The inverse of a matrix is dividing by that matrix, essentially. And when you multiply them together, you should get the result of 1. And what you really get is the identity matrix, which is 1, 0, 0, 1. Okay, I'm kind of just giving you some of these things as definitions. There's a whole lot more in matrix theory to understand. But what we're looking for is two matrices that multiply to equal 1, 0, 0, 1. So everybody, let's try it on your calculator. I want you all to type in matrix A and then times matrix A with the inverse. Give it a shot. Matrix A times matrix A and then hit x inverse. And what do you get? So everybody try that on your calculator. Does it work out? 3, 1, 0, 0, 1? Great. Yeah. Yeah. Uh-huh. Oh, did I forget?
No, like.
Oh, good. Oh, good, you figured it out. Way to go, Cisco. Yeah, 1, 2, 3, 4. Okay, very good. Wait, yeah, that's already your matrix. 1, 2, 3, 4. That's your matrix. So then, what we want to do is that matrix A, and then we're going to multiply it times matrix A again, and then inverse. That's the two. Let's see, hit it. Did it work? What it says there? Oh, you were trying something else. Okay. Did it work? Did everybody get 1, 0, 0, 1? Okay. Now, this matrix that we just got, the 1, 0, 0, 1 matrix, it's called the identity matrix. This is the identity matrix, much like the number 1 is the identity. Because, going back to algebra, anything times the number 1 is itself. And any matrix, like the 1, 2, 3, 4 matrix, times the identity matrix, 1, 0, 0, 1, will just equal itself again. So that's the role that the identity matrix plays, is that if you take any matrix and multiply it times this 1, 0, 0, 1 matrix, you get back the exact same matrix again. So the 1, 0, 0, 1 matrix is called the identity, and that is what defines a matrix and its inverse. So given any matrix, its inverse is the matrix such that when you multiply them, it equals the identity. And so what your calculator is going to do for us right now is find the identity of, it's going to find the inverse of all those matrices. So let's try a couple more. First of all, did everyone write down the solution for A inverse? So A inverse was this one. So let's try B.
doesn't compute.
It does not compute. But regardless, everybody go ahead and try it. I want you to see what you get when you do this one. So if you all go back into your matrix and type in matrix B, which is 6, 14, 15, 35, and go ahead and try to compute matrix B inverse. So go into matrix, go over to edit, go to matrix B, and then this is a 2 by 2, and you'll type in the numbers 6, 15, 14, and 35. Once you have that matrix in, then you go back to your main calculator screen and choose matrix B, and then X inverse. And once you finish typing all that in, it says error, singular matrix. And what that essentially means is that that particular inverse has no inverse. That matrix has no inverse. As a quick note, what I'd like you to write down for this problem, part number 2, is this system is either parallel or overlapping. Right? So that's part of how matrix theory is going to relate back to the original work we were doing about a system either being intersecting, overlapping, or parallel. When we convert our systems into matrices, if you go to compute a matrix inverse and it says error, that means the original system cannot be solved. It's either parallel or overlapping. Only if when you do the inverse, you actually get an answer, does that tell you that you're actually able to find the point of intersection, that there's just one point of intersection and you're about to find it. Okay, let's try one more. Let's just define the inverse of matrix C. So this is 3, 2, 3, 0, 1, 2, 4, 3, 5. And we'd like to find C inverse. Now keep in mind, this is the most laborious part of what we do with matrices, is just typing it into the calculator. So while you're sitting there thinking, oh man, I have to hit second matrix, go to edit, go down to C, change the size to 3 by 3, and then type in all those numbers, again going left to right from top to bottom. So 3, 0, 4, 2, -1, -3, -2, -5, typing them all in. Yes, it is time consuming and laborious to type all this in, but isn't it better than doing all that work by hand? Right, that's the trade-off. So now that you've got it typed in, you can go second matrix, choose the name matrix C, hit X to the -1, and everybody, your matrix inverse should be -1, 8, 4, 1, 1, 1, 6, 8. So take a moment and find the inverse of matrix C. Oh, goody. Yeah, let me know if you have any questions. I want to come around and help you. Oh, really nice. And in fact, if this one came out with the lowest decimals, you can hit math, right? In fact, you can go back in time. What matrix was that? Well, maybe you've already over it. I'm not sure. Anyway, at that point, if you hit math, right, you can remove those subtractions for you. No worries. Nice. Did it work, did you? Okay. Oh, very nice. So you've got your 3 by 3. It's 304, 2, -1, 3. And then you very good. So then you hit second click, go back to this screen. There's your C, and then you just hit X inverse right there. There you go, did that. That's it. You did it. Very good. So did it work? Yeah. Okay, here's. Did it work? All right. Okay. Now, at this point, you might feel like we're doing so much magic. Like, you know, what is the relationship of all of this to reality? What does all this matrix computation mean? It might seem pretty arbitrary. Well, let's go ahead and try a problem, because I think we'll be pretty excited to see the answer. So let's see, on your packet, turn to, the very next page where it says try again using inverse methods. I want to do one problem before we take a break, because I want you all to see it, and then we'll take a break. Okay. First, just find somewhere on your page where you can write this very simple algebra equation down with me. Let's say that you had the equation ax b. How would you solve for x? You just divide by a, right? And so you divide by a, and in normal algebra, you have x equals b divided by a. That's what it would look like in normal algebra. In matrix algebra, you have ax equals b, and whoop, write that with a little more space. Write down ax equals big space b. In matrix algebra, we still want to solve for x. We still want to solve for x. But we want to cancel that A matrix. And the only way to, quote unquote, cancel out the matrix is to multiply it by its inverse. So watch, if I now multiply on the left, both of these, by A inverse, then what happens here is that the A inverse times A, a matrix times its inverse, equals the identity matrix, which we write by writing the letter I. But like I said, anytime you multiply any matrix by the identity, you just get that original matrix back. And so ultimately, you can solve any matrix, any system of equations, by just computing A inverse B. So now let me give an example. Let me take a look here. Here we go. Oh. Oh no. X plus Y equals 1. Is it that one? X plus Y and 2x minus Y. Okay, good. I'm just gonna write it down. So let's consider the equation x plus y equals -1, and 2x minus y equals -5. Okay, so that's where you are on your page. Do you have that problem pulled up in front of you? Sorry, let me just hold this out. So everybody's looking at this page right here where it says, try again using inverse methods. And so we're all looking at the top left problem. Okay, well first, let's convert this system of equations into a matrix. Okay, over on the left-hand side, if you put in all those coefficients, we would have the matrix 1, 1, 2, -1. That's our A matrix. Over on the right-hand side, we would have a very small matrix, -1, -5. And that's our B matrix. And what this is the equation AX equals B. So from your original system, which is already written in standard form, where you have x on top of x, y on top of y, equals on top of equals, and number on top of numbers. You take the coefficients from the variables, and you make your A matrix. You take your coefficients from the right-hand side of the equal signs, and you make that the B matrix. And that is exactly what you're going to type into your calculator. You're going to enter the A matrix and enter the B matrix. So everybody go and do that on your calculator. Enter the A matrix and enter the B matrix. So matrix A will be 2 by 2, 1, 1, 2, -1. What's the size of matrix B, by the way?
It's 2 by 1.
Yeah, 2 by 1. 2 rows by 1 column. So your matrix B, edit, matrix B, 2 by 1, -1, -5. So what we're about to compute is our solution to the algebra problem. It will be A inverse B. So on your calculator, now go ahead and compute A inverse times B. So second matrix A, x to the -1, times second matrix B. And just to check your answer, you should get that. When you multiply A inverse times B, you should get -2 and 1. When you're all done typing in matrix A and matrix B, and then you compute A inverse B. 2 by 1, because it's 2 rows, 1 column. So, credit, 2 by 2 is 1, 1, 2, negative 1. That's correct. So then, oops. 2 by 1. Oh, yeah, negative 1, negative 5. Oh. There you go, negative 5. Okay, now try that again. Okay, did it work, folks? Did you get negative 2 and 1? Let's see. 2 by 2. That's good. 1, 1. Oh, that's correct. You got it. And then your second matrix should be 2 by 1. 2 by 1. Which we're going to put in negative 1 and negative 5. Now, negative 1 and negative 5. Okay, so now you have it. Now now we're going to multiply A inverse times B. Put it to negative 1. So you're going to do matrix A inverse times matrix B. That's it. Did it work? Okay. Work? Okay. All right. Brandon, did it work? Okay. Joseph? Victor? Isaac? Okay. Okay. Good looking? Okay. All right, so folks, what you just found, so when you have your final vector here, that is your answer for x and y. It represents it as a matrix right there, but what they're saying then is that x equals negative 2 and y equals 1, and therefore the coordinate is negative 2, 1. And that's the answer to the system. Okay, that was a lot of information all at once, especially if you've never seen matrices before. That was a very, very fast introduction to matrices. I think we should go ahead and take a break, and then when we come back, we'll continue solving more matrices with inverses, and especially the 3 by 3 matrices, which is the big payoff of being able to solve a 3 by 3 matrix without doing all those hand calculations. You just type it into your calculator. It's very fast. So let's take a break. It's 9:20. Let's come back at 9:45. I'm sorry, 9:30.
Look on the announcements. I didn't see the practice test solution.
Oh, thank you for telling me that.
I just see the solutions for the chapter 8 and 9.
Oh, right, but not the practice test. Okay. Sure enough. All right, Abe, it's there. Thank you. Yeah, the practice test solution. Yeah, thanks for pointing that out. Oh. All right, Ed, that was all there. All right, folks. All right, we covered a lot of information right there. So now that we have the basics of how to type a matrix into our calculator, let's look at fresh eyes here at these next couple problems that are on your page and set them up really nice and neat so you see how to do this consistently. So
I actually just need to look at a copy. Oh, my copy's still here. We go. Okay, so we're all on the page where it says try again using matrices. All right. So number 2, I suggest we all try formatting it the same way. Number 2 says x plus 3y equals -3, and 4x minus 3y equals 18. And so this first chunk becomes the first matrix, and then the second chunk becomes the B matrix. So this would be your A matrix, and this would be your B matrix. Okay, that's just me kind of making a note to myself. So we're all on number 2. So I'm going to go and write down that A is equal to the matrix 1, 3, 4, -3. And B is equal to the matrix -3, 18. Now again, this is the power of the calculator, this is the power of matrix, that we're taking a system and we're completely sidestepping the idea of solving with substitution, elimination, graphing, any of those methods whatsoever, and just extracting the coefficients from those 2 equations, and then simply entering them into the calculator and finding A inverse B. And whatever the answer to A inverse B, that is the answer for X and Y. This solves the system. So probably for anybody that has access to a calculator, this would be the preferred method for solving a system of equations. You know, faster than elimination, faster than substitution, faster than graphing. So into our calculators we go. We're going to edit matrix A, which is 1, 3, 4, -3. And then back in to edit matrix B, which is a 2 by 2 matrix. This is a 2 by 1 matrix, right? Okay. So then my 2 by 1 matrix is 3, 15. And then you go back to your main calculator screen and you're going to multiply matrix A inverse times matrix B. And you should get 3, -2. So go ahead and do all that. Type all that into your calculator. Multiply A inverse times B, and see if you get 3, -2. There it is. Oh, wonderful. It worked. Okay, that's super. Great. Folks, what do you think about this matrix method? Would you prefer doing this than substitution and elimination?
Yes.
Yeah, and you're just typing things into a calculator. I have to admit that for all of its simplicity, you know, because everything is a give and take, right? Like, if you save effort in one area, it must be extra effort in another area. You don't get anything for free. What do you call it? You don't get a free lunch. There's no such thing as a free lunch. So instead of doing all of that work with substitution and elimination, where you knew what you were doing and why, we now have this method, which appears to save us a lot of energy, but right now we have no real understanding why this works, right? Is there anything about this that makes intuitive sense, like why that should work? No. So we sacrificed understanding for something that works and quickly, right? So there's a little bit of irony here. It does work though, right? We just don't know why it works. We would need to spend a lot of time and weeks studying matrices to see why this works. Okay, well, should we try another one? We could try 4 or 5, but I think maybe since those two are pretty similar, well, yeah, okay, let's try 4 real quick, just so everybody can check their work. What's interesting about number 4? What do you have to be careful about? In number 4, they write the variables out of order, don't they? I don't know if you caught that. But the variables have to be stacked on top of each other. So number 4 should actually be written 5x plus 1y equals -7, and then 2x plus 4y equals 8. If you had already solved it the other way, with those variables swapped, you probably did get an answer. But if you plug that answer into the correct variables here, it wouldn't actually have created 2 true equations. So now that the variables are written in the right order, with x on top of x, y on top of y, number on top of number, now we should be able to say that A is 5, 1, 2, 4, and B is -7 and 8, and
And so A inverse B is equal to, I don't know yet. The nice thing is, now that you've already typed A inverse B into your calculator, once you edit A and B and you go back to your main screen, you can hit second enter. By hitting second enter, it brings back up A inverse B already. And when you hit enter this time, it will compute the A inverse B of the updated matrix that you just edited. So that's nice that you don't have to keep on typing in A inverse B. This answer was -2, 3. So that means that the answer for x and y, like let's go one step further and actually write down what the answer is. The answer is the coordinate -2, 3. Now again, see here, this is even more fascinating. That we're looking at two linear equations, meaning we're looking at two lines in space. And I don't know what those lines look like. If they're positive sloping, negative sloping, I have no idea. But I know that they intersect at -2, 3. At least I think they do. Do I know that for sure yet? No, I don't know that for sure yet. I actually have to plug -2 and 3 into my system. So now if I do that, that would be -10 plus 3 is -7. That's true. And then here, plugging in -2 and 3, that's -4 plus 12 equals 8. That's true. Okay, so yeah, it did work. So I'm just going to lap through them one more time. Please let me know if you have any questions at all about typing these things into your matrix. Did it all work out? Yeah, sure did. Now, as a side note, when you take your test and you get to a problem that says solve this system using substitution, do you have to use substitution or can you just use your matrix inverse? You do have to actually solve it by substitution and show me all the work. But can you check your answer by using the matrix inverse? Yeah, like so now, as of now, you now have a magical calculator method for solving any system of equations, so you automatically know the work. So what is the matrix? There's matrix B, which is what you get into this matrix. Yes, I do. And then go back to here. Okay. All right. Well, folks, number 5, I'd say you can go ahead and do on your own. Now, when you turn the page, try again using matrix methods. Oh, okay, that's fine. When you turn the page, you're going to see something called determinants and Cramer's rule. Let's come back to that. And in fact, we might not even do that because the inverse method is really what's most exciting here. So we'll come back to that. Let's move forward. And I wanted to try one of our 3x3 matrix. Well, and I guess we don't have to. But no, let's do it because it'd be fun. Let's go back a couple pages to where we did a 3x3 matrix. Like, yeah, like here. Let's go all the way back to this one. Let's try typing it into your calculator and seeing if it works. I mean, obviously it should, but I want you to have the experience of doing a 3x3. So all the way back now to our 3x3 systems. And number 1, notice that the variables are already written in standard form. So you've got x's on top of x's, a stack of y's, and a stack of z's, and then the numbers on the other side of the equation. So if we write this down now as matrix A, which is 3, -1, 1, 2, -4, 3, 1, -1, 1, with matrix B being 3, 16, and 5. All right, so we're just going to try one 3x3 matrix because I want you to see that the real power of this inverse method is the fact that it'll work on any number of variables. So if you had 4 equations and 4 variables, 5 equations and 5 variables, 10 equations and 10 variables, you could simply use your calculator to use this inverse method. And that's incredibly powerful because it's such a time-saving device. So we're simply going to compute now A inverse B and see if we get the same answer we got last time. So make sure you update the size of your matrices now. The sizes now are 3 by 3 and 3 by 1. Which of course you have to update it because otherwise you wouldn't be able to type in the data. So and again, you already had A inverse B in your calculator, so you can just hit second enter and then enter again. And I got the answers -1, 0, and 6. Which, if you're on the same page that you were when you did this problem, you'll recognize those are the answers. Those were the answers for X, Y, and Z. Now, you all remember solving this problem the first time around. Remember, it took up a huge chunk of the page. Now look how much work it took up on the page. Just enough work to write down the A and the B matrix and then write down the answer. Isn't that crazy? I mean, it's wild that you can get the answer that quickly, that your calculator is that powerful. This is probably one time in your life where you're like, whoa, calculator is really powerful. Like, I just got to skip all that work and just get the answer. Okay, did it work for everybody? Everyone got the 3 by 3? Now again, this method that we're doing right now, I would call it at this point magic. All right, we gained speed, very little work that we have to do on our part, but we have no understanding of why it works. And if you ever take another class in, like say, matrix algebra, then you'd get to understand why it works. But for now, we just used it as a calculator tool. Okay, well, let's see. We did section 8.4. Oh, those are my 3. Oh, yeah. We're going to come back to determinants and Cramer's rule. We may or may not even cover it. It's just another matrix method, but the inverse method is the most fun. So let's go ahead and take a look at 8.7. We'll just hold off on section 8.5. We may or may not get to it. I mean, it is still fun. I hope to. All right. So we're at systems of nonlinear equations and inequalities. So in 8.7, you'll notice I gave you lots of space. I've got all the equations on my screen right now, but you've got multiple pages here. Did I just choose a couple of these? You have 1 and 2. I didn't give you number 3. You have 4 and 5. Oh, that's all I gave you. Okay, so I just gave you some of these. I didn't give you all 8 of those problems. But let's go ahead and just go in order of your 4 problems, 1, 2, 4, and 5. And those are the ones we'll do. So everybody, take a look at number 1. What is that? And what are we trying to solve? Like, just look at how they wrote this down. X squared minus y equals 4. And x squared plus y squared equals 4. What does that mean, solve? Right, we've been talking about solving systems of linear equations, but let's just go back to the definition. What does it mean to solve a system? All right, we're solving for x and y. And what will it be that we're solving for? Now, coordinate. What coordinate? Yeah, we're looking for the intersection point, right? So whatever this thing looks like, which I think it's parabola, whatever this thing looks like, I think it's a circle. If you graph them both simultaneously on the same graph, there might be a point of intersection. Okay? And let's just consider, will a parabola, everybody go ahead and write it down in your own words. Is a parabola? It's a circle. Will a parabola and a circle intersect? I mean, maybe. I mean, if the parabola and the circle look like that, no. If the parabola and the circle look like that, no, they don't intersect. But if the parabola and the circle look like that, then yeah, they intersect. If the parabola and the circle look like that, then yeah, they intersect. Or if the parabola and the circle look like that, then yeah, they would intersect twice. Could a parabola and a circle intersect more than 0, 1, or 2 times? I don't know. I mean, maybe. What if the circle went like that. Then could I get 3 intersection points? In fact, if the parabola looked like this and the circle looked like this, could I get 4 intersection points? Yeah, well, ooh, this is pretty exciting, right? There's a lot of different ways for a circle and a parabola to intersect. So how many solutions are we going to have? Wait, infinite? Could we have infinite?
Why is it would be infinite? It would be a set.
How many points of intersection could we have? None, 1, 2, 3, or 4. That's just as far as my imagination took me. Could we get 5? Could we get 5 points of intersection out of this? I don't think so.
What if the circle,
Sitting.
what if like the curvature of the parabola was like the bottom half of the circle, then it would be overlapping like half the circle? Does that make sense? Or could that not happen?
You've got a circle and then what happens?
Yeah.
Yeah, so the parabola.
No.
So it's
No,
the
but
parabola is
but
like.
make it go like up more, right? So like, no.
No, so
What
like the
communication
parabola,
style?
if you wanna go on the
Why don't you
side.
draw it for me, please? Like draw it over on your board there, Brandon, and we'll all take a look at it.
It'd be like, if it was like this,
Yeah.
but then the circle, like, was going like that.
So there's
Oh, and
one
like
part
somehow the
that's-
So, but like
curvature?
But like perfectly, but it would be like overlapping on like.
Right. Okay, now that's okay, very interesting. Is that what you meant, Selena, and other people? Okay, that's a fun question. Could the curvature of the circle, so could that curvature right there match exactly the curvature of some part of the parabola? Is that what you're asking?
Yes.
Yeah, no. Okay. That's a great question, and it doesn't happen that way. There's no chunk of the curvature of the circle that exactly matches the curvature of the parabola. I can't exactly prove that to you right now, but it wouldn't be the case. It would only ever match 1 point at a time, but not for a section of it. But that was a great idea. That was a really nice idea. It just doesn't happen to me. Okay, so back to the question, how many intersection points are we going to have? We have no idea. Right? We have no idea how these are going to intersect. All we know for sure is that it's going to be 0, 1, 2, 3, or 4. So what should we do? Graph it, right? I mean, that's probably the easiest way, is just to see immediately what we're looking at. And in this particular case, we have this. And so how many solutions do we have? 4. So this particular problem ended up with 4 solution points. Now look at these solution points. 2 of them are nice, negative 2, 0, and 2, 0. That's easy. Whereas the other ones are negative 1.732 and positive 1.732. And those happen to be the square root of 3. I just happen to know that. There's no way that anybody should happen to know that. But 1.732 is the square root of 3. Okay, so we have 4 intersection points, and that's what we're expecting from this system. So everybody go ahead and draw that now. Just so you know what solution you're looking for. There was solution points here, and then here, and our circle, well, was going through that. It doesn't have to be perfect, but that was 2, 0. That was negative 2, 0. That was negative root 3, negative 1. And that was root 3, negative 1. Right? Yeah. Now, to be fair, if you're allowed to use technology, you're done with this problem, right? If you're allowed to use technology, you're done with this problem. If this was your actual job and somebody handed you that system, you just go put it in Desmos and you go back to the boss and be like, there you go. Those are the points of intersection. However, we'd like to see how to do this using algebra. So, my suggestion to you is that you're either going to use substitution or elimination. And because we can't do this with a matrix, first of all, because that's an x squared, that's an x squared, that's a y, and that's a y squared. So these aren't even the same types of variables, like that's a y and that's a y squared. But more importantly, you can only use the matrix method if it's just x, just y, just z. Right? It can't be x squared or y cubed or anything like that. Okay, so matrices are only for linear components, x to the power of 1, y to the power of 1, z to the power of 1. Okay,
So we need to use substitution or elimination. So which do you think would be easier? Well, we could do substitution like if we solve for y. Remember, substitution, you need a substitution sentence. So right now I could say y, and I could solve for y right here. Don't write this down. I'm just going to show you that this would be an unfortunate way to go. Not that there's anything wrong with your guess, Chelsea, but I think that this would end up being a little harder. So if I solve for y, I would move my x squared over. Then I have negative 1y equals 4 minus x squared. And then I divide off the negative 1, or I multiply everything by negative 1. And I get y equals x squared minus 4. So now I know that's what y is. But what do I have to substitute that in for? The other equation's y. And what's the first thing I'd have to do to x squared minus 4? I have to square it. Can you even imagine? If you had x squared plus something squared, and what do you have to square? X squared minus 4. Now all of a sudden, you're looking at x squared plus, FOIL that out, x to the 4th minus 8x squared plus 16 equals 4. And now we have an x to the 4th term? This would be a little more challenging than we need. So at that point, you would say, okay, hold on, let's not do substitution. This is taking me down a road I don't want to go. Instead, let's try elimination. What can we eliminate very easily? Yeah, the x squared term. Look at the x squared term. This one has a 1, this one has a 1. So I've got the same variable, x squared. They both have a 1. We just need one of them to be negative. So let's try that. Which one should we make negative? Sure, the top one. Now remember, you can multiply all the way through by negative 1, or you can just change all the signs. So I'm going to change the signs from positive to negative, negative to positive, and positive to negative. And now I can go ahead and do elimination. Elimination will often be the method we'll choose for doing nonlinear systems. Cancels out the x squareds, and now we have y squared plus y equals 0. Well, how do we solve that? First of all, this is a parabola, and it's quadratic. So you could either do the quadratic formula, you can do a, b, and c, where this is really 1y squared plus 1y plus 0. And you can say a is 1, b is 1, c is 0, and do the quadratic formula. Or better yet, you can just factor, right? What can we factor out of y squared and y? Just a y. And now this is the zero product rule. I have this times this equals 0. And therefore, either y equals 0 or y plus 1 equals 0. Which tells us either y is 0 or y is equal to negative 1. Now, was that solution better than that substitution thing we attempted? Yeah, big time. Now, who's going to tell you that? Nobody. You just try different methods. You know, you try substitution, looks nasty, turn around, try elimination. Try elimination, looks nasty, turn around, try substitution. There's no... But now what do we do? These are both possibilities. Both are possible. So what do we do then? Yeah, we're going to plug it in. So the first thing I would do is say, let's just do one at a time. So coming over here now, let's say y is 0. Okay, that's one possibility. If y is 0, then what? Then what's x going to be? What can I plug y into? Either. Right? You can always choose either one. Let's choose the top one because y is simply y. I'm going to go back to my original signs. Wasn't it x squared minus y equals 4? So I'm going to plug in 1x squared minus y equals 4. And I'll go ahead and plug in 0. So what does that give us? X squared equals 4. And therefore, x equals what? Plus or minus 2. Now this is really interesting. If y is 0, then x can be either plus 2 or minus 2. And therefore, what coordinates are we talking about? If y is 0, x could either be 2 or negative 2. So that one possibility of y equaling 0 actually generates 2 different coordinates, which are the 2 different coordinates we saw on our graph. So this is really interesting, right? By doing elimination and solving for y, there were actually 2 possibilities for y. And here it is. Each possibility of y has 2 possibilities as well.
So now that we're done with that, let's keep going. And let's say y is -1. So if, let's say, well, I think I made a mistake. It's not √3, it's √5. Gosh, let's say y equals -1. So that's the other possibility. Then again, I say let's plug it back into the first equation. So x squared minus something. Oh no, it is √3. Okay. And I'm going to plug in -1. So that's a double negative. So chop chop. X squared plus 1 equals 4. So subtract the 1. X squared equals 3. And you square both sides. And x could equal plus or minus √3. So now in this case, we're saying if y really is -1, we had two possibilities. If y was -1, then x is either positive √3 or negative √3. And if you type that into your calculator, √3, you get that decimal we saw earlier, which was 1.73. So 1.732 -1 or -1.732 -1. There. I'd say the most interesting part about this is how the number of solutions explode. Right? Instead of just one point of intersection, we got 4 points of intersection. Where did the 4 points of intersection come from? Why were there 4 instead of just 1? What unique feature allowed us to get 4 possibilities? There are 2 different things that happened that took us from merely 1 solution to 4. What was the first thing that happened? The fact that we had y squared, so there's 2 solutions, and it was a 0 product rule, so there were 2 possibilities. Right? So that was the first kind of splitting of solutions. Where did the other splitting of solutions come from? The fact that you square rooted and you got a plus or minus. So that's really interesting, these features. Okay. Well, that was number 1. And number 1, we just happened to use elimination. So what's the next problem? Number 2? That's mine, number 2, and your number 2. Okay, great. Let's take a look at that. All right. In number 2, we have x squared plus y squared equals 16. And 16x squared plus 4y squared equals 64. Now, before we do anything at all, thinking about substitution and elimination, let's just ask ourselves, how many times could these things intersect? Well, first of all, what are they? This first one is a circle, and the second one is an ellipse. A circle is a perfect circle, whereas an ellipse is a squashed circle. So how many times could a circle and an ellipse intersect? There could be 4 times, right? If you had like that happening, that would be the maximum, 4 times. But it could also just be 3 times if the circle touched down on it and went through those. Or it could just be 2 times, or it could just be 1 time, or it could be no times, right? So those are all the possibilities. Do we know which one we're dealing with? We have no idea. So what do? We graph it. I hope that I've put this idea in your mind enough now that this is what you do in your own possible life. You'd be like, not quite sure about this problem. Let's graph it. Let's go see what it looks like. There. So what was it? Yeah, it looks like just 2 points of intersection, right? What does this graph look like? To me, it looks like a cat's eye. Does that look like a cat's eye? Maybe. Okay, well, in any case, everyone draw a picture and write down what our solutions are. The solutions are 0, 4, and 0, -4. So go ahead and draw a picture. Always helpful to know ahead of time what we're dealing with. So there's my graph, there's my squashed circle, and my regular circle, and it's a 0, 4, 0, -4. And again, if you were allowed to use technology, you would just be done. But the purpose of this is for you to show me the algebra.
So what algebra are we going to choose? Substitution or elimination? Yeah, elimination might be our best thought, right? Because we've got these x squared variables and these y squared variables. So we could eliminate the x squared variable. That's a positive 16x squared, so I could make this a negative 16x squared. Or that's a positive 4y squared, I could make that a negative 4y squared. So which one do you want to eliminate? Doesn't really matter. How about let's eliminate the x. So I'm going to multiply this whole top thing by negative 16. And that'll give us negative 16x squared minus 16y squared equals negative 256. And that'll eliminate the x squareds. And then we have negative 12y squared equals something. Negative 192. One other thing I hope you've noticed is that, the original problem statement looked pretty tricky. X squareds, y squareds, like imagining doing algebra on that. And yet, how powerful was the elimination method? How amazing that so quickly we got rid of one set of squared variables. And then all you have left is just dividing out the coefficient. And we have x squared or y squared equals 16. Even though the original problem statement was quite sophisticated, the elimination method takes us to an algebra problem that's pretty quick and simple. So y is either plus or minus 4. And does that agree with what we found out from the picture? Yeah, y is either plus or minus 4. Okay, so now what? It might be helpful to write it like this, 4 comma negative 4. Because now we have to consider both possibilities, right? It's kind of like two alternate realities. So I'm going to come over here and say, let's say y is 4. Then which equation should we substitute in for? The first one or the second one? Oh, the first one, right? The first one doesn't have any of those coefficients. So I'm going to take my x squared plus y squared equals 16. And I'm going to plug in 4 for y. So that's x squared plus 4 squared equals 16. And so x squared plus 16 equals 16, which the 16s cancel, or subtract them off. And you get x squared equals 0. Notice this time when we did the square root, does plus or minus 0 give you two different answers? No, because positive 0, negative 0 are the same thing. It's really just x equals 0. So that's just one possibility there. When y was 4, x could only equal 0. So one of our coordinates was 0, 4. Right? Unlike that previous problem, when you got to the end and you did your square root, you actually got two different answers, which gave you two different answers for that one possibility of y. Here, that one possibility of y only generated one coordinate, not two. So then you proceed and you say, let's say y is negative 4. And then you try that possibility. Because remember, the first solution gave us y was 4 or negative 4. So you have to try both. So if we say y is negative 4, again, x squared plus y squared equals 16. So x squared plus negative 4 squared is 16. You end up with the exact same equation. X squared plus 16 equals 16. The 16's cancel, you have x squared equals 0. And when you square root 0, there's just one possible answer, which is 0. So that gives you the other coordinate of 0, negative 4. Okay, well, let's try another one. In fact, we'll do both of these. So number 4, everyone take a look at number 4. What is it? Yeah, the first one's a line. What's the second one?
Circle.
Is it a circle?
Well, the first one's a circle, the second one.
Where is it? Is it
It's
not
x
there?
squared plus y squared equals 16 x minus y.
Oh, yeah, yeah, yeah. How would you know that? Here's the thing, on your calculator, in order to graph anything, it has to be y equals. On your graphing calculator screen, you go to that button that says y equals, and then you have y1 equals, y2 equals. The other way that you can graph anything is if you solve for y first. So like unlike me, x squared plus y squared equals 16, I can just plug that into Desmos and it'll just show me the picture. You'd actually have to take x squared plus y squared equals 16, and you'd have to first solve for y to get y squared equals 16 minus x squared. You have to square root both sides, and then you'd have y equals plus or minus root 16 minus x squared, and you would actually have to plug in y1 is positive root 16 minus x squared, and you'd have to graph negative root 16 minus x squared, and then your graphing calculator would actually show you the circle. So a TI is a little limited because you actually have to solve for y first, and if there's a plus or minus, you have to graph both chunks of the curve. And on your graph, this part is the top half of the circle, and this part is the bottom half of the circle. So if you wanted to try that on a TI, you can. It's just a little bit more laborious than Desmos, where I can simply type in, yeah, there it is already, x squared plus y squared equals 16. In any case, there's that one, and our line, x minus y equals 2, cuts right through it, and there's one intersection point, and there's the other. Now notice, and I'm sure all of us are thinking, well, gosh, if I really had to do this for a job, I would obviously just find all these points of intersection using Desmos. Why would I do any algebra at all? But look at the point, 3.646, 1.646. Do you think that those answers are accurate? Are they? I mean, how accurate are they? It's only accurate to 3 decimal places. And do you even believe the third decimal? That third decimal could be wrong, right? Just looking at that, for each of those answers, I'll just take the 3.646. First of all, the actual answer could be 3.646, 52937, etc., out to infinity. And all I have is 3 decimals of accuracy. But even worse, the real answer could have been 3.64592937, and it rounded. So these answers from Desmos, are they high quality? These are not high quality answers, because at most you have 3 decimals of accuracy. At best, you probably only have 2 decimals of accuracy, and the third digit is rounded. So it's kind of like, thanks, Desmos. You're kind of trying to help me out, but you're not really giving me the decimals of accuracy. So how do you get the decimals of accuracy? You have to do it by hand, right? That's why we learn to do it by hand, because just using Desmos only gets you so far. It gives you an idea of what the answer should be, but to get the actual solution, you need to do it by hand. So, everybody, x squared plus y squared equals 16. We have our answer already. It's that, right? And the other one is x minus y equals 2. Okay, now what? The first 2 problems we did with elimination. Can we do elimination now? Yeah, we actually cannot, because you can only do elimination if it's the same variable. And that's an x squared and that's an x. So we can't do elimination. That's a y squared, that's a y. So we can't do elimination. So you can't do elimination, so what are you going to do? Yeah, you're going to do substitution. And you can either solve for x or y. It's your choice. So what should we do? Solve for x or solve for y? Probably x, because it's already a positive x, and we just have to move the y over. So everybody, let's move that y over there. So now we have a substitution sentence of x equals y plus 2. Now maybe you could totally solve for y too, as well. You know, either method is going to work. Okay, so now what? We have our substitution sentence. We have to plug it into the other equation, and we have to write it empty for the variable x. So our other equation is something squared plus y squared equals 16. And then we plug in the y plus 2. Now, you know how I said if you try one method and it starts to look pretty nasty, just back up and go back and try the other method? Like right now, you can't just say, oh no, this looks pretty nasty, let's not do it this way. Because we already agreed we can't do elimination. Right? So sometimes you just have to push forward and do what's in front of you, even if it looks a little nasty. So what do we have to do? Here we have to square the y plus 2, which means to FOIL it. So we're going to FOIL that out. Now, if you can FOIL it in your head, that's great. If not, just use a little scratch work somewhere else. So you'd say, okay, y plus 2 times y plus 2. And you FOIL that out, so it'd be y squared plus 2y plus 2y plus 4. And then combine like terms. So the answer is y squared plus 4y plus 4 plus y squared equals 16. Now what? Yeah, we have to combine like terms. So we have 2y squareds, and then plus 4y plus 4 equals 16. And how do we solve every quadratic? We have to move everything over to one side, set it equal to 0. Because that's how you would either factor it and use the zero product rule or do the quadratic formula with A, B, and C. So we'll bring the 16 over. And we can do one more thing to make our life easier. What's the one more thing we can do to make our life easier? We can divide out 2. Because right now, if you look and try to factor that, you'd say, oh no, there's a coefficient on the y squared. I'd have to multiply by 2 times 12 and do that factor table. But the fact is we can just divide everything by 2. So now that gives us y squared plus 2y minus 6. And now there's a possibility we can actually factor this thing. Can you multiply anything that equals 6 that you can add to make 2? What multiplies to make 6 that adds to make 2? Nothing. So you'd use the quadratic formula. I wonder if in your mind you see all this happening, almost like a video game where you're like doing battle. Like in a video game, like you're fighting a bad guy and you're like, should I use my sword or should I use my gun? And then like the next stage, and you're like, should I use my nunchucks or should I use my, kick him? At every point you're just deciding, how do I do battle against this? And that's essentially what we're doing here. We're like, okay, should I do elimination or substitution? Move forward. Okay, now turn it into a quadratic. Do I factor a quadratic formula? Factor. Okay, can I factor it? No. Okay, quadratic formula. Like you're constantly making these decisions. Like, how do I attack this? How do I attack this? And this is why it's so important that you just have all these methods floating around in your brain, right? Well, I can do elimination or substitution, factor, quadratic formula. But there's so many possibilities. You almost need a piece of paper written down somewhere that shows you your list of arsenal, right? Like these are all the things I can do.
Aren't you missing the 2?
What?
You have to put the 2 in front of that.
I just divided out the 2. I just divided everything by 2. Is that okay? Okay, so now we would have A is 1, B is 2, C is -6. We do the quadratic formula, so x equals negative b plus or minus square root of b squared minus 4ac all over 2a. And plugging all that in, we have 2, 2, 1, -6, and 1, which is -2 plus or minus 4 plus 24 is 28 over 2. Now I know I only have 5 minutes left, but we also only have a couple problems left, 3 total, provided we're skipping the determinants. We may or may not come back to that next week. But to finish this problem, first of all, you could just type that in your calculator and get 2 decimals. And if you do, you get the decimals 1.646 and 3.646. But there is one more thing we could do to the root 28. What can you do to root 28? You can simplify root 28. What square number goes into 28? The square numbers are 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. What square number goes into 28? 4. So that's really 4 times 7, which is root 4 times root 7, which is 2 root 7. So now we really have -2 plus or minus 2 root 7 over 2. Or what can you do with all the 2's? You can divide them all by 2. So that's a 1, that's a 1, that's a 1. And we're left with -1 plus or minus root 7 all over 1, but that's really just -1 plus or minus root 7. So I want you to notice that that really is a better answer. -1 plus or minus root 7 really is better than -2 plus or minus root 28 all over 2, which is why it's important to learn how to simplify roots when you can. So trying that on our calculator,
negative 1 plus root 7, I get 1.645751311. And what did Desmos say? 1.646. And then the other answer was negative 1 minus root 7, which was negative 3.645751311. And Desmos said negative 3.646. So this is a really great problem that shows that Desmos, can really only be trusted to 2 decimal places. And Desmos didn't even tell you that the answer, the exact answer. Boy, that'd be cool if Desmos could tell you that. But it can't. By the way, what is this problem asking us to find? X and Y. Ooh. So we still get to go back and solve for Y, folks. But fortunately, do we have a nice formula for Y? I'm sorry. Wait, we just solved for X? No, we didn't. We were solving for Y. I wrote down X. Oh, shame. That was Y that we just solved for, right? So do we have a simple formula that will solve for X? Yeah, our substitution sentence. Remember, that's actually the value of the substitution sentence, is that as soon as you're done solving for Y, or one variable, you get to use your substitution sentence to immediately tell you your other variable. So look how easy this is. If Y is negative 1 plus or minus root 7, then X would be just Y plus 2. So you just add 2 to that. Okay, but we do have to go one step at a time. Okay, we're almost done. We're going to finish this problem and then we're done. The fact is, though, how many possible answers do we have for Y? 2. So let's start here and say, let's say Y is negative 1 plus root 7. Okay? Then X equals negative 1 plus root 7 plus 2, which is really 1 plus root 7. So that's one coordinate. So 1 plus root 7 and negative 1 plus root 7. That was one possibility. But then we have to say the other possibility. Let's say that Y is negative 1 minus root 7. So that was one. Now we'll say, let's say Y equals negative 1 minus root 7. Then X is going to be negative 1 minus root 7 plus 2. You see where I'm getting that, right? Because it's X equals Y plus 2. So now that's 1 minus root 7. So then that last coordinate would be 1 minus root 7, comma, negative 1 minus root 7. Okay. So those are our 2 final coordinate answers. Because you had to carefully piece together both of the coordinates from the equations. I hope that you tried writing that down, the whole let's say thing, because you're just kind of setting yourself up to write down the solutions carefully and slowly. Okay, well, were there 2 points of intersection? Yeah, there they are. Just look at the signs. That's a positive number, that's a positive number, and that was that solution, plus, plus. And then down here, that's a negative number, that's a negative number. That was this solution down here, minus, minus. Okay, let's talk about next week. Your homework is only to finish, because we didn't do section 8.5 today, right? That was, we totally did do inverses, so you will do that section, but not 8.5, okay? But as far as the 8.7 section, you could go ahead and do section 8.7. Okay, so your homework due Monday is all chapter 8 except 8.5. Okay, that is what is due on Monday. And then next week when we come back in, we're going to start class by just wrapping up a couple problems that we didn't look at together, like maybe section 8.5 on determinants. But we might just move forward and do chapter 9. Okay? So everybody, that's what's due next week. If you have any questions, please come see me. I'm in my office for the next 2 hours. You can also email me anytime. I gave a calculator to a few of you. Please bring those calculators back up. Thank you, Isaac.
Oh, was that next one? Okay.
I think I need 2 more calculators. Thanks, Sis. I'm glad I figured out your calculator. Thank you, Brandon. Brandon, bring in your calculator. I want to try to fix it. Thank you. There you are.